Okay, here are some more of the problems from the Chapter 7 review. Let's take a closer look at 3, Part C. You're supposed to find the exact value of the sine of pi over 12. Well, again, from the note card, you don't have pi over 12. I do, however, have a pi over 6. So, referring to the back of the note card, I have a half angle formula that tells me it's plus or minus the square root of 1 minus the cosine of the bigger angle divided by 2. So in this case, I'm saying that pi over 12 is equal to pi over 6 divided by 2. So the sine of pi over 12 is equal to, now let's deal with this plus or minus thing here. That sign, the positive or negative symbol in front of the square root will be determined by the quadrant of the final angle. So in this case, well, pi over 12, that's first quadrant. I'm going to take the positive square root. So then I need 1 minus, I'm going to use pi over 6 here, so I need the cosine of pi over 6 is square root of 3 over 2, and then again, all of that is over 2. Okay, so that's a substitution using my half angle formula. Now, okay, it's the struggle here to simplify. So since I already have a denominator of 2, I'm going to convert everything so it has the same, a common denominator, and get rid of that. So 1 is 2 over 2 minus square root of 3 over 2, and then 2 over 1 would be 4 over 2. I can simplify numerator and denominator independently. Leave alone the one that you can't simplify. Simplify the one that you can. And that would be sufficient. Again, just write it like we normally do. I think sometimes they print things with the answer key in a form that's more friendly to how the book is physically actually printed. They've got enough troubles with the square roots, and in this case, nested square roots is what it's called there when we have a square root under another square root symbol. So the fact that they put a coefficient of 1/2 out front, I think, again, that's just preference there in the printing process. I would prefer you guys just leave it like this. There seems to be no advantage of taking that 2 from the denominator and rewriting it as a coefficient. All right, let's also take a look at both parts of number 5. We're asked to write sine 3x times the cosine of 5x as a sum of trigonometric functions. And then part B, write the sine of 2x minus sine of 5x as a product. All right, so we have our product to sum and our sum to product formulas there. All right, so for part A, sine times cosine was, I believe, the very first one in that particular lovely blue box. So sine of 3x times the cosine of 5x, according to my formula, should be 1/2 times the quantity. I need to take the sine of u plus v, so in this case that means adding 3x plus 5x, plus the sine of u minus v, so 3x minus 5x. So again, that coefficient of 1/2 stays where it is, simplify inside the parentheses. So this is the sine of 8x plus the sine of, oops, negative 2x. Well, we can get rid of that second set of parentheses, so we don't need the brackets anymore, if we acknowledge even odd functions here. Sine of negative theta is equal to the negative of sine positive theta. So I can turn this from sine of negative 2x into minus the sine of positive 2x. So again, that even odd function is how that went from what should be an addition into a subtraction. And then for part B, we have sine of one angle minus sine of another, rewriting this as a product. Okay, so again, that's in that same section a little bit further on down. The difference between the sine functions. So sine of x minus sine of y. So sine of 2x minus sine of 5x should be equal to 2 times, now again, get the right formula. It's the subtraction one for two sines, should be the cosine of basically the average. We're going to add 2x plus 5x divided by 2 multiplied by the sine of half of the difference. So I'll take 2x minus 5x divided by 2. So then, okay, just simplify what's on the inside of the set of parentheses there. So this gives me 2 cosine of, well, that's an odd number. So I'm just going to leave that as 7x over 2. And then, okay, order of operations matters here. That's negative 3x over 2. But again, quit being so negative all the time. Let's write this as positive angle measures. So again, just the even odd functions that I showed you there a moment ago for part A. Let's pull out a negative in front, 2 cosine 7x over 2 times the sine of, now that becomes a positive 3x over 2. Now, please, the last thing I want to see here is some kind of confusion. Sine of 8x. I don't know what x is, but I know sine of 8x refers to a specific value. Sine of 2x, all right, it's a different angle. They're multiples of some value of x. But the sine of this angle and the sine of this angle, those are not like terms. Never, ever, ever, ever try and take that and distribute here, okay? The coefficients there will affect the values of sine or cosine. It will never directly impact the angles. Please don't do that. I know it's tempting. It looks so simple, like we should be able to, no, no, don't do that. Number 8, find all solutions in the interval from 0 to 2 pi, not included, rounded to 5 decimal places. Well, isn't this going to be a joy? All right, algebra. Let's divide both sides by 5. And I'm going to give myself some more room to work here. It looks good in the book when it's centered, sure. is equal to 2/5. So again, I have the variable term isolated. I've got the coefficient of that down to 1. Now I need to take the inverse cosine. 2/5, otherwise known as 0.4, is not on your calculator. I'm sorry, it's not on your note card, so we need the calculator. Oh, I'm just a little bit tired. I'm sorry. So we'll take the inverse cosine of 0.4. Give me the decimal approximation, please. So the 1.15927, blah, 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 this is approximately 1.15927, That's not theta. That's 2 theta. Okay. But again, standard operating procedure here, we should add our standard plus 2k pi, or, now again, our other option here is cosine's positive in the first quadrant, which is our first set of answers there, but cosine is also positive in the fourth quadrant. So I need to take 2 pi and subtract this value to give me the starting point for my second set of solutions. 5.1239, etc., etc. Sorry, not equals, approximately equals 5.1239, blah, 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 plus 2k pi. Once we have those angle measures established here using the inverse cosine, then we'll take care of the fact that it's not set equal to 1 theta. Okay, if that's in this case 2 theta, 17 theta, whatever, dividing to get this down to the value of theta should be taken care of after you take the inverse function and find both sets of solutions. Okay. So that then transforms these into, again, we're going to divide everything by 2. And hopefully you can see this makes a difference here. So theta is approximately, now I've got to go back to the 1.15927,948 divided by 2. So that'll give me approximately this, 5796, 0.5796 plus 1k pi. And then the second one there, meh. Okay, yeah, great. I've got this on video here, how I make mistakes sometimes. Yeah, I'm taking half of 5.123. There's no way that that's 0.23. All right, now, all right, divide that by 2. 2.56. 2.56195, blah, 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 plus 1k pi. That seems much more reasonable. All right, so now that I have my expressions, then I can get around to finding the values here in this particular interval. So for the first one here, we're going to have k set equal to 0. And then we're going to have k set equal to 1. And then we're going to stop because having the interval here from 0 to 2 pi, substituting 2 in place of k, that's going to give us values that are too big. Okay? So if I just take that previous answer and add pi while it's there, it's at this point where I'm going to do the rounding. I'm not going to do that way back at the start there. I'm going to do the rounding as my final step. So 5.7035. Oh, that was close. That has to be rounded up to 5. And that actually is going to turn out to be the biggest, the last of my answers. $5.70355. 2 point, go back and read this again here. 2.56195. All right, that's the fifth decimal point, that 2. That'll round that one down. Now the very first one, going back to, no, not where I divided by 22. Going back up to this one here, rounding that off to 5 decimal places, 0.579639. That should round up to 64. So 57964. And now to that one is what I need to add pi. And take that and add 1 pi. And then round that off. 3.72123. Again, messy numbers made more technical by the fact that they wanted 5 decimal places here. And again, I caution you, don't round off to 5 decimal places when you're at this step here. Don't round it off to 5 decimal places even when you're at this step here. Okay? Let the calculator, as best you can, deal with the messy numbers. Let it add pi going past the number of decimal places that is requested. And once you've established this out to 6 decimal places, then you can round it off to 5. Okay, don't do the rounding too early. And then we'll wrap this up with number 9 here. Exact value of the cosine of 2 times the inverse tangent of 9 over 40. So again, we've talked about this before. When you see this expression, an inverse function, that means some angle. Okay? So this is really just another way of saying find the cosine of 2 theta. I don't really need to find out what theta is. Time to draw a picture. Now I'm told that the tangent is 9 over 40. So like opposite 9, like adjacent 40. Now, again, if you don't remember this, you'll have to go through Pythagorean theorem, but this actually does turn out to be one of our Pythagorean triples. If one leg is 9 and the other leg is 40, the hypotenuse turns out to be exactamente 41. Nice whole numbers here. So now, cosine 2 theta, well, we have several different options there for our cosine function for double angles. One option that we have, well, I don't know. Let's try the first one. Cosine squared of x minus sine squared x. Either of those other two formulas should work equally as well. I'm not sure if there's really an arithmetic advantage in this problem of choosing one over another. So for our value here, the cosine of theta, leg adjacent divided by the hypotenuse, which should be 40 over 41, and I will square that. And then I have to subtract. No, this is not a Pythagorean identity. It's not sine squared plus cosine squared. This is the difference, and order matters. Now I have to subtract sine, which would be 9 over 41, after I square that. Well, isn't that convenient that even after squaring them, I'm going to have common denominators? If I take 41 and square it, that gives me 1681. So 40 squared, well, 4 squared is 16. There's one 0. I'm squaring it, so I double the number of zeros. Nine squared is 81. Take the difference between those, and that'll give me 1,519 over 1681. Not a value that you run into every day, but in this case, it's the exact answer. Okay, I think that pretty much sums it up here. When we get together next week for the test, might do one or two things to just quickly refresh your memory, jumpstart that trigonometry part of your brain, and on to the test. So I hope this helped. See you guys soon.